Hi everybody! So in today's video, I'm going to be talking about the idea of accumulation functions. Some of what we discussed today will be a review, and some of it will be a way to kind of combine two of the things we've learned, which is the features of a function looking at a graph, as well as accumulation functions, which we talked about in chapter 6. So as a review, an accumulation function is a function that is defined as the integral of another function. An example of what an accumulation function might look like is this one. F of x is an accumulation function and the reason it's an accumulation function is that f of x is calculated by integrating a new function g. Now, one of the things we learned in chapter 6 was how to take the derivative using something called the fundamental theorem of calculus. And we're going to review that now because we're going to need this in order to take the derivative for some of the questions involving accumulation functions. So as a review, our rule for taking the derivative using the fundamental theorem of calculus was that if you take the derivative of a function like this, that f prime, which is the derivative of the left side of the equal sign, will be equal to, and on the right side, we said when you take the derivative of an integral, they just undo each other. They're inverse operations. So we'll end up just dropping in the x into the function. So it's going to keep the g, and we're just going to make it an x. And if necessary, we would use chain rule to take the derivative of the bound only. So since the derivative of x would just be 1, we don't need to worry about it here. We also don't need to worry about the 2 because the derivative of the number 2 is just 0. Another example of where you might use the fundamental theorem to take the derivative would be like this one. So the derivative of the left side would be f prime of x. And the derivative on the right side, I would just take the 4x and drop it in because a derivative and an integral are inverse operations. So that means we're still just going to have g at the end. It's going to undo each other. So I would have g of 4x. But then I would need to multiply by 4 by the derivative of the bound that I just plugged in. Again, I'm not going to worry about the lower bound, the 2, because the derivative of the number 2 is 0, so that part doesn't matter. For the last example here, the derivative of f would be f prime of x. And on the other side, the derivative of 6x would just be 6. And the derivative of an integral, they undo each other because they're inverse operations. So I would just have g of x. So my derivative this time would be 6 plus g of x. Now we're also going to be going back to some of our graph sketching vocabulary from way back in chapter 5. So let's review some vocabulary words that we use to talk about graphs. So one of the things that we talked about was the idea of a critical point. A critical point is a place where the derivative is equal to 0 or does not exist. And our derivative is not going to exist when we have corners, cusps, vertical tangents, or discontinuities. If we're looking at the graph of f prime, so if the graph of the derivative is shown, we're looking for the x-intercepts. Those are going to be the places where my derivative is equal to 0 because those are the places where the y value of the graph is 0. We use the word increasing to describe functions that have a positive slope. So we're looking for parts of the graph. So f prime of x would be greater than or equal to 0. If you're looking at the graph of f prime, these are places where you are above the x-axis. Decreasing means that our graph has a negative slope. These are going to be places where the derivative is less than or equal to 0, or places on the graph of f prime where the graph is below the x-axis. Now, when we move on and we start talking about the second derivative, a point of inflection is going to be a place where the second derivative changes signs. So when I change from having a positive second derivative to a negative, or from a negative to a positive, that's going to be considered a point of inflection. If we're looking at the graph of f prime, these are going to be at maximum and minimum values because the second derivative would be the slope of f prime. So we're looking for where the slope of f prime changes signs. Now, concave up is a specific vocabulary word that we use to describe functions that have a positive concavity, so a positive second derivative. They're concave up. This is going to be greater than 0, the second derivative. On the graph of f prime, it would be where the graph of f prime has a positive slope. Which we can sometimes just use the vocabulary word increasing to describe that. So when the graph of f prime is increasing, we are concave up. When the original function was increasing, the graph of f prime is above the x-axis. Concave down would be used to describe a graph that's down like a frown, which are going to be places where the second derivative is less than 0. So this is going to be the place where the graph of f prime has a negative slope. Or we can describe that as decreasing. Now, all of this combines to allow us to talk about things like extrema. So we said extrema is a word for maximums and minimums. Relative extrema must occur at places where the first derivative changes from positive to negative. So if your graph is going uphill and then changes to downhill, you're going to have a relative maximum. Now on the graph of f prime, this is going to be a place where the graph of f prime changes from above the x-axis to below. One important thing about a relative maximum is we don't consider the endpoints. If we're talking about a minimum, this would be a place where your graph has a valley. So the first derivative would change from negative to positive. Or it could be a place where the graph of f prime changes from below to above the x-axis. Again, we don't consider the endpoints when we're talking about relative extrema. And that's important because there are times when we do consider the endpoints. If we're ever talking about what's called an absolute extrema, so the absolute maximum or minimum, these are going to be places where f prime changes signs either from positive to negative or negative to positive. The only way to determine what the absolute extrema are is to make a table where you have your x values and you have your y values, and you actually pick out which one's the biggest and which one's the smallest. In this table, you need to make sure to include the critical points and the endpoints. So this is why it's important to know when you consider endpoints and when you don't, because this is an example where you do consider the endpoints as x values in your table. All right, that was a brief, very brief review of some of the things we've learned already this year, and we're going to continue to discuss these ideas in the context of an accumulation function. So let's start by reading the instructions. One key piece of information that you need to know about the AP test and about our test is a lot of good information is contained in the instructions. So a lot of times the directions will actually give you clues about what you should be doing in the actual problem. It says, let f be a function defined on the interval from 0 to 7. The graph of f, consisting of 4 line segments, is shown here. Now, g is going to be the function given by g of x equals the integral from 2 to x of f of t. So, if part A says, please find g of 3, what this means is take the number 3 and plug it into the g of x equation everywhere that you see an x. This is a review of something we did in chapter 6. So I would have the integral from 2, and then I'm going to replace this x with a 3, of f of t dt. Now you want to make sure to show your work here. One of the things that is often on the AP test in the rubrics is that you can receive partial credit as long as you're showing the intention behind the work. So don't ever just jump straight to doing the answers. You want to make sure to show the work the same way I'm showing the work in my answers. Now, in order to calculate this integral, I'm going to go back to what it means to have an integral, which is an area. So the integral from 0 to 3 would be the area of this graph between 0 and 3. So stopping here. I'm going to break this up into two parts, the triangle at the beginning and the trapezoid. So my area is going to be 1/2 times the base of the triangle is 2 times the height is 4, plus for the trapezoid it would be 1/2 times the height is 1 and the base is 4, the other base is 2. So I would get 4 plus 4 plus 2 is 6, so half of that is 3, which equals 7. Now part 2 here, part B, says find g prime of 3. You should never just jump straight to finding g prime of 3. Instead, you want to show your work here. Oftentimes on the AP test, showing the function for g prime of x will earn you partial credit. So if I want to find g prime of x first here, taking the derivative of this integral, I would just drop in the x, which means I would have f of x here. Which means that if I want to find g prime of 3, I would replace the x with a 3 in this equation. Now, f of 3 just means find the y value of the graph when x is 3, which on this graph would just be the number 2. Last but not least, and this is a review question again, find g double prime of 3. Again, you never want to jump straight to just finding the answer. You want to write down the second derivative and then plug in your number. So I'm going to go back to here. The second derivative would just be the first derivative of f. So I took the derivative again on the left side, I took the derivative of the right side. Now I'm going to plug in the number 3. F prime of 3 means the slope at the place on the graph where x is 3. Now this slope is going to be the slope of this line segment. So to find the slope, I'm going to rise 4. The run will be -2, which means the slope would be 4 over -2, which is just -2. Now, these first 3 questions should be a review of something we learned in Module 6, or Chapter 6, where we're going to start kind of making it one level deeper is we're going to say, for example, in Part D, identify where g of x is increasing and decreasing. To figure out where g of x is increasing and decreasing, we need to look at g prime. So g prime of x, which I already calculated in Part B, is just f of x. In other words, this graph of f is really the derivative graph of g. If we're looking at the derivative graph, then we can figure out where we're increasing by looking for where this graph is above the x-axis, which would be from 0 to 4 and from 6 to 7. My justification would be because g prime of x, which is equal to f of x, is greater than or equal to 0. Now, there are a couple important things about this justification. The first important thing is I'm talking about g prime, but I need to then relate that to the graph that I've been given, which is f. So it would not be enough to just say g prime, and it would not be enough to just say f. We need to show a connection between the function that we are being asked questions about, which is g, and the function that we have a graph of, which is f. That means you need both pieces of that explanation in order to get full credit. Now I'm going to be decreasing for the portions of this graph that are below the x-axis, which would be from 4 to 6. And I would say because g prime of x, which is equal to f of x, is less than or equal to 0. It's negative. For part E, it says find the x coordinates of the critical points. Now, critical points are places where the derivative is equal to 0 or undefined. Determine whether each of these points is a relative maximum, minimum, or neither. So as a follow-up question, for each of the critical points, tell me if there's a max, min, or neither at that location. So let's start with critical points. Critical points are going to be the places where g prime of x, which in this problem is really just f of x, is equal to 0 or does not exist. Now, based on this graph, there are no places where the derivative does not exist because there are no places on this graph where there is a hole or an asymptote or something that would tell me it doesn't exist. Which means I'm really just looking for places where the derivative, which is just f of x, is equal to 0. So that would be 0, 4, and 6. Now, the follow-up part to this question is to determine for each of these values whether there's a min, a max, or neither. So let's start with 0. At x equals 0, which is the beginning of my graph, there is going to be neither a min nor a max. And the reason is because it does not change signs there. Not it. G prime does not change signs. There's nothing happening before this. So we would say at x equals 0, there is neither a min or max because g prime of x does not change signs. Now let's think about 4. When x is 4, the function g prime changes from positive to negative, from above to below. If we change from positive to negative, we're going to have a relative max. So we would say at x equals 4, there is a relative max because g prime of x, which is really just f of x, changes from positive to negative. Now you might be wondering, do I have to say all that? Do I have to say positive to negative? And the answer would be yes. And the reason is because if it changes from negative to positive, it's not going to be a max anymore. Last but not least, at 6, we're going to have a min because the graph changes from negative to positive. So we would say at x equals 6, there is a relative min because g prime of x, which is equal to f of x, changes from negative to positive. All right, let's look at a couple more things that we can do using one of these graphs. So find the x coordinates of the points of inflection. Points of inflection are places where the second derivative changes signs. So we need to think about the second derivative of g. Based on our previous problem, we know that the second derivative of g is really just f prime, so the slope of the graph that we're given. In other words, we need to know where the slope of this graph changes signs. So we are going to have a point of inflection when x is 2 and when x is 5, because those are the two places where the slope of the graph changes from positive to negative slope, and then from a negative to the positive slope. So we would say points of inflection at x equals 2 and x equals 5 because the second derivative of g, which is just f prime, changes signs. As a follow-up, the next question asks us to specifically talk about where we're concave up versus where we're concave down. So we're looking at the sign of g double prime. And the second derivative of g is just the first derivative of f. So we are going to be concave up whenever we see a positive slope on our graph, which would be from 0 to 2 and from 5 to 7. And we would say because the second derivative of g, which is the first derivative of f, is greater than 0. We can also say we're concave down whenever our slope is negative, but there is one place where I'm going to need to break up this interval. I've got a downhill slope and a downhill slope. I need to exclude this corner because derivatives don't exist at corners. So I would say from 2 to 4 and from 4 to 5 because the second derivative of g, which is the first derivative of f, is less than 0. Last but not least, find the absolute maximum and absolute minimum. In order to find an absolute maximum or an absolute minimum, we need to consider the critical points as well as the endpoints. In this case, that means I'm going to consider 0, 4, 6, and 7 because those are endpoints and critical points. So in my chart, I'm going to include 0, 4, 6, and 7. Now, in order to determine which of these values is actually the biggest, I'm going to need to find the y value of g. So to find g of 0, I need to integrate from 2 to 0. Now, the integral from 2 to 0 means I'm going to the left, which means it's going to be negative, and it would just be the area of this triangle right here, which would be 1/2 times 2 times 4. So that would give me -4. To find g of 4, I would need to integrate from 2 to 4 of f of t dt, which means it's the area of the triangle on the other side, but I'm going in the right direction. So it would be 1/2 times 2 times 4, which is +4. To find g of 6, I would integrate from 2 to 6, which means start with that same triangle I had here, so 4, but take away the little triangle below, so 1/2 times 2 times 1, which would just be 3. And then to find g of 7, I would have the integral from 2 to 7, which means I have the big triangle above minus the little triangle that was below, plus the little triangle that's above at the end right here. So 1/2 times 1 times 1, which gives me 3.5. From this list, the highest number is the 4. So I would say that I have an absolute maximum at x equals 4 because that's the associated x value. And the lowest number is the -4. So I would say that I have an absolute minimum at x equals 0. I did just notice one mistake I made earlier in this video. I really apologize for doing this. I'm going to go back and just explain that one real quick. So in this problem, I was only supposed to integrate from 2 to 3, and I went all the way from 0 to 3. So the mistake here is I should not have included this area. It would have just been the 3. So that was my bad. I apologize. All right, thank you guys so much for watching. I hope you have a wonderful afternoon, and I will see you tomorrow for some practice.